class. This is 6 on the chapter 10 practice test. Let me share my screen. So this one was an essay type of question. And so I'm going to kind of like just do, I'm going to do sort of like a similar problem. I'm just going to I'm going to change some of the numbers a little bit from this particular problem. So I'll just say 5 years. And I say this is 4 years, just to make everything easier for me too. I'll say this is 1 year, the standard deviation here is 1. And I'll say the standard deviation here, I'll just say 1.6. And then I'll say 2. I'll leave everything else the same. Okay. A researcher was curious to see if students who attended community college first and then a 4-year university after took longer to graduate from college than students who went straight to the 4-year institution. Here's the resulting data. For students who attended community college first, 265 students were sampled, and the mean of their graduation was 5 years, with their sample standard deviation of 1.6. For students who went straight to the 4-year university, 1,134 were sampled, and their mean graduation was 4 years, the standard deviation was 1. Does the evidence suggest that community college students take longer to graduate from college? Okay, so is this a mean problem? Are we comparing two population means, or are we comparing two population proportions? That would be our parameter of interest right here. And so we would, at this point, it's a really good idea to identify what parameter, the proportion or the mean, are we interested in. Remember, the parameter is like the value, either your average or proportion, but coming from the entire population of interest, not from just a simple sample. The parameter is something that we rarely have information about because we don't want to sample that many people. We don't want to sample 15,000 people. We don't want to make that many phone calls. So we do a smaller sample, right? So that is what the parameter is, coming from the entire population. So that's the one we're usually trying to estimate with the confidence interval, or trying to just test with hypothesis testing like this. So hopefully you identified this is a mean problem, right? Whenever they say average or mean, and here I can tell it's a mean because they say that well, let's see, that the mean time to graduate was 5 years at the for the community college students. And then the mean for the straight to the 4-year institution was 4. So, and then does it take longer to graduate from college? So how are we going to see if something's longer? Well, we're not going to use that with the proportion. You'd said they have to come out and kind of say, hey, the proportion of these people is larger than those people. No, but they're not doing that in this case. They're just saying, hey, who went to school longer? Well, how are we going to say a group of people went to school longer than the others? We're going to have to compare the averages of those two populations. So this is definitely a mean problem, and they give us the data from, or not the data, but the stats. Mean they give me this mean, and the shortened version of the data. The actual raw data is like all of these 1,134 people sampled. What you could list out all of their responses when we ask them how long it took them to graduate, right? That's a lot of it. That's a raw data. They just give us the average of that data and the standard deviation of that data. So that's the stats coming from that data. So this is a mean problem, and they already gave us the averages. So sometimes when they give you the raw data, then this might be a matched pair design type of mean problem. But because they just give us the stats from the data, there's not even a possibility that this is a matched pair design. This is definitely an independent mean problem. So we'll use a two sample t-test to do this problem. And so, the first step is they say state the null hypothesis. And probably even before that we do that, they let us, you've got, before you start saying making variables and writing variables in formulas and in mathematical sentences, we've got to tell everyone what we mean, tell ourselves what we mean by that variable, and we have to tell everybody else. You just can't say, well, 5x times 7, 5x minus 7 is equal to y. And you're just like, everybody's like, what is y? And what is 5? Or what is 7? What is x? Like, I'm sorry, what is x and what is y? So that's something very important. Every time we write a variable down, we should clearly define what is that variable, what does it represent? Okay, it's called defining your variables. So I already kind of did that for you. I said, let U of t, and I really meant U sub t, and I meant like mean, the mean of the transfer students, be the population mean number of years it takes for students who attend community college first and then transfer to graduate. Okay, so that's the community college mean. Okay, so mu t for transfer students. Okay, then you let U in t, so I went like the mu sub n t be the population mean of taken of non-transfer students. So NT is non-transfer. Okay, so then it says, does the evidence suggest that the community college take longer? Well, if the community college takes longer, that would mean that the transfer student mean average to graduate would be higher, a lot bigger than the non-transfer student. So that's definitely what we want here. The mean of the transfer student is bigger than the mean of the non-transfer student. So this is the alternative hypothesis that I already kind of stated here. So now we need to state the null hypothesis. Well, the null hypothesis and these tests are always just equals. So the same expressions that we saw in the alternative hypothesis, but just equals. That's our null hypothesis. Okay, so that's part A. Part B, state the p-value. So they just want us to go straight to get the calculator and get that calculator to calculate. So it's a 2-sample t-test that we want. They tell us, and they can remind us, x bar 1 means the first mean sample, and SX1 is sample standard deviation of the first list, and then N1 is the first sample size. And then they want everything with that same thing, but also from the second population. So just so that you know, right? And this is what I was talking about earlier, that when we placed the UT on that left-hand side, we really meant that's our population. One is the transfer students. Because it's what we listed on the left side of the null hypothesis. And then population 2, so every time over here, when it says 1, subscript 1, those are all data coming from the transfer student data, okay? And then everywhere it says 2, that's the one that we listed on the right side of the null alternative hypothesis, and that is going to be in our situation the non-transfer student, okay? So let's write down our information that we need to do the p-value test. So x1, that's actually, I'm going to use the t, and so it's xt. That's x bar t and s t, so an nt. And then we have x nt, s nt, and NNT, okay? So this is transfer, non-transfer, and this is transfer student data. So we go back up to the problem. The average time it took them to graduate from college for the transfer students, for students who attended community college first, 265 students were sampled. The mean time was 5 years. Okay, so 5 here, and the standard deviation I think was 1.6, but let's go back up. 5 years with sample standard deviation of 1.6, so 1.6. And then the sample size I think was 265. Hey, beauty. Oh, you look cute. Look at what you're wearing with the little mermaid.
Do you know how I got this song all by myself?
Okay, hold on. Let me pause.
Do you know how?
Sorry about that. Okay, now next, XNT. That's the non-transfer students. For students who went straight to the 4-year, the ones who went straight to the 4-year, right? The sample size was 1134. So let me write that in. Darn it. And then the sample standard deviation was 1, and the sample mean was 4. Okay, so now I have all of this information. Now, all I have to do is input it into the calculator. Oh, sorry. And do the calc and do this classic calc test. So X bar, okay, wait. So sample 2 test. Okay, so we said that the transfer students were on the left side of our hypothesis, so they are the ones that wherever there was a 1, we're going to put that population. So 5, 1.6, and 265. Okay, then all the number 2s are all our NT. So 4, 1, 1, 1, 3, 4. All right, so we go to class calc and we input all this information. And then we look at the alternative hypothesis. So let's go up, and it is, you just have to look at the direction that this alternative hypothesis is going in. So notice that it's pointing to the arrow. If you think about it as an arrow, it's pointing to the right. So we have to make sure that we pick the value that is pointing to the right as well. And it's this p-value there, which is 0. So in our situation, our p-value is approximately 0. So just so you know, we did a 2-sample t-test, and our p-value is 0. That one's not going to be hard to compare to anybody. All right, part C of this problem. I accidentally wrote that in the pink. All right, we go back up to the front of this problem. And we found that, okay, and so the next step, okay, we interpret the p-value. So the interpretation here is that the likelihood of us having, of these samples being from the same population having the same mean with that large of a difference is 0. The probability that they're from the same population is 0, which means that these are definitely coming from different populations with different means, which means that that Fresno City College students, the transfer students do have a longer time than the other students. So let me write that out. Let me see if I can write that out in the interpretation of the p-value. Is the probability, and you could say it of these two populations, and here I mean the transfer students. That's population 1, right? And non-transfer students. Having the same average graduation time is 0, right? Because well, let me restate this, and the probability of these two populations we'll say it this way: the probability of these two populations having such a large difference in samples is probability of these two populations having such a large difference in sample means and being and when they came from a population with the same mean, same population mean is 0. So it's so unlikely, it's practically just impossible, basically. The only way that these two samples could come from a population that had the same average hours or average years of going into spent in college is so unlikely that it's impossible, basically. We're saying the probability of these two populations having such a large difference in means when they come from a population with the same mean is 0. Okay, that's our interpretation of the p-value. Because the p-value, and then let's draw a picture of it, and then drawing a picture of it may help you guys to even further understand this question. So in a difference problem like this, when we're doing this two population, two sample problem, what they do is they find the difference between the two means, and they find like the z-score of that difference and find out how many standard deviations away from the mean is this difference. And then they give us this test statistic z based on, it's basically based on the difference between the two means. The larger that difference, the farther away from the 0 in this distribution it's going to be. So they give us actually a t. I'm sorry, because it's a t distribution, means have t distribution, not z distributions like how portions have. It is a t distribution. And there's a distribution of the sample differences. Well, of the sample mean differences. So the larger that difference is, the further out in these tails that this value is, this z-score is going to be. The further out in these tails, the more unlikely, because this is like a frequency distribution. All the, if in fact the difference between the means is the difference in the means of the population is 0, like we assume to be true in the null hypothesis, then most of the samples are going to come back with a difference of 0 or really close to 0. So that's the most common one to happen if the means are the same from the two populations. However, the larger that difference between the two sample means is, then the further out in the tails, it's going to be either in this direction or this direction, depending on whether you're taking the large number minus small or the small minus large. You're going to be either in this tail or in this tail. But the further out in the tail, the more evidence against the null hypothesis that they actually have the same means, because most of the data should be, in the center area, if in fact they have the same means and population means. So what we do is we place the test statistic. It's the number of sample standard deviations that this sample, the difference of the samples is, and then we calculate the area under the curve. And oh, wait a second, I think this, let's look back. I think this, it was, right, is it a, yeah, oh, I'm sorry, this is a right tail test. So it's actually the other side. And actually our T value is 9.7, which is humongous. So I'm sorry, I'm on the wrong side. So I'm on the negative value side. And actually, it's over here, way over here. So our p-value is like right here, and it's almost nothing. The area under the curve past this z-statistic. The z-statistic is our lower bound of the area under the curve, and the area under the curve is our p-value. In this case, they're saying it's practically 0 area under the curve to the left, to the right, sorry, to the right in this right tail test of this z-test statistic. And the z-test statistic they told us was 7.89. Look at this test statistic. See the 9.73. So this is actually the right picture for our particular problem here. The value along the x-axis is the z-test statistic, or sorry, t test statistic, sorry about that. And then, which is 9.73, and then the area under the curve was practically 0 because that t value is so large. Remember that 95% of the data is within 2 standard deviations. So that's like 2 is probably like back here. And the t distribution is kind of similar to the z distribution. That's with the z distribution and the normal distribution, but this is a t distribution a little bit different. But like still, most of the data is within 2 standard deviations of, and then, so when you're at 9.73 standard deviations above mean, you're really far out there. So this is really, really strong evidence against the null hypothesis that it's very, very unlikely to come from the same the population, the same mean or the same population. All right, that's a picture, and that's the picture. That's the values that we want. Okay, then it says state my decision. So part D is because the p-value is less than alpha, which is, what is alpha in this problem? Oh dear, did I not put alpha here? Just curious to see if the students attended community college first and then before you're going to here, those data, this and for those who went to straight university, mean time is 4 years, is this suggests ahead, but and then okay, I forgot to put a level of significance here. So I'm just gonna say 0.05. And it doesn't really matter because let's let alpha equal 0.05. It doesn't really matter because no matter what it is, it's going to be, the p-value is going to be smaller because p-value is 0, rounded to 0. So because the p-value is less than alpha, we reject the null hypothesis. That's our decision. Then it asks us to state your decision. Are you ready to know? They state the conclusion. And now we just, the very final conclusion here, we just say, because whenever we reject the null hypothesis, we always say there is sufficient evidence. There is sufficient evidence for whatever we were trying to claim in the beginning of this problem. There is sufficient evidence to support that the mean time for transfer students to graduate is longer than non-transfer students. And there we go. That's our final conclusion here. All right, please let me know if you guys have any questions. Sorry, I did not put in there a alpha. I forgot that. All right, have a great day. Bye.